Uh, I'm sorry, I just realized I didn't turn on the recording. So let me turn on the video recording. And yeah, let's replay the video so that the video recording is more complete.
Hi, Professor. Is there any sound in the video? Because I cannot listen nothing.
Oh, anyone else cannot hear the sound?
No,
Yeah, there's no sound.
No sound?
No, but you have the link in the PowerPoint, so you can just copy the link and
Same for me.
view
No.
the video.
I just shared the sound. Now, can you hear it? Can you hear it?
Yeah.
Music? Okay, good. I'm glad that you brought it up. So it's a short video, so let's watch it.
The technology being developed for driverless vehicles is pretty incredible. In the near future, there will be robotic cars traveling on normal roads with the safety and efficiency of the best human drivers. These autonomous vehicles use various sensors to be able to localize themselves in any environment. They are also then able to construct a detailed plan to get from their current location to any desired destination. This video will provide an introduction to how these autonomous vehicles are then able to follow their desired trajectories. Getting a vehicle to follow a trajectory may seem simple to those who have driven before, but is it? Let's take a deeper look at this in a lab setting. If we want to follow a line, but we are too far to the left, we turn to the right, and vice versa. But how much do we turn? If the steering wheel is turned a fixed amount to the left or to the right, the approach is called bang-bang control. For controlling a car, this doesn't actually work that well. The response is very jerky and uncomfortable for the passengers. Fortunately, we don't have to steer like this in a car, since there is a range of angles the steering wheel can take. One way to set the steering wheel angle is to use what is called proportional control. Rather than turn the wheel a fixed amount, proportional control steers harder the further away we are from the desired trajectory. We take a measurement called the cross-track error to define how far away from the desired trajectory the vehicle is. Therefore, the steering angle we use is this cross-track error multiplied by a scaling factor called the proportional gain. The range of values the proportional gain can take drastically alters the performance of the vehicle. As you can see from this overlay, the performance gets better as the gain increases, but at a cost. If you start too far away from the desired trajectory with a high gain, the system can spin out of control. With the best gains, proportional control returns better results than bang-bang control, but it still doesn't work that well. With proportional control, the car can be crooked when it reaches the center line. The result of this is that the controller will repeatedly overshoot the actual desired trajectory and not actually follow it. To correct this overshooting problem, we need to consider additional error measurements and use them to update our steering command. A good candidate for an extra measurement is to look at the cross-track error rate, or in other words, how fast we are moving in a perpendicular direction with respect to the desired trajectory. If we are perfectly following the trajectory, our cross-track error rate will be 0. In control theory, this is what is called a derivative term. This rate term can then be multiplied by its own gain and added to the proportional term to construct an updated controller. Now that we have two terms, we have two gains that must be tuned simultaneously. Conceptually, we can think that increasing the proportional gain will increase the pull that the vehicle feels towards the desired trajectory. Increasing the derivative gain increases the resistance the car will feel against moving too quickly towards the line. Fixing the proportional gain, if the derivative gain is too low, the system will be what is called underdamped and it will still oscillate. If the derivative gain is too high, the system will be what is called overdamped and will take a long time to correct for offsets. Properly choosing the derivative gain allows the car to approach the desired trajectory quickly with a cross-track error rate close to 0. This is called being critically damped. Despite the success so far, for a complete controller, we're not done yet. Environmental factors or mechanical defects can change the vehicle's nominal behavior and thus the performance of the controller. For example, if there's a heavy crosswind, the vehicle will drift unless the driver counteracts this wind force with a corrective steering command. Here is an example we can easily demonstrate. Imagine our vehicle is driving along and hits a pile of rocks which knocks its front end out of alignment, and therefore a 0 steering command no longer keeps the vehicle driving straight. As you can see, with the controller that has been described so far, the vehicle experiences a buildup of a lane offset, or a steady-state error. One way to address this problem is to add yet another term called an integral term. This third measurement sums up the cross-track error to give an indication if we are spending more time on one side of the trajectory or the other. You can see that if we sum up the cross-track errors, we obviously spend more more time on one side of the trajectory. The integral term we propose is then exactly this sum multiplied by a gain. Now, 3 gains will need to be tuned all at once, which can be quite difficult to do by hand. If the gain is too large, the controller can go unstable because normal controller fluctuations will be exaggerated. If the gain is too small, it can take too long to respond to these dynamic changes. When the gain is just right, the controller will be able to quickly correct for the front-end misalignment and return to its nominal performance. The combination of these 3 terms is then what is referred to in control theory as PID control. There are other more advanced controllers that can be used for self-driving cars, but they will all look similar to the one we have described in this video. There will always be some measurements made about the state of the vehicle, which are then compared to some desired vehicle trajectory to construct a steering angle that ultimately controls the car. Hopefully this gives some insight into the control strategies that can help make self-driving cars possible.
So that's the basic intuition behind PID control. So PID control has 3 terms. So first, you get the error term from the difference between the reference and the measured output. And then your goal of the controller is to let the output of the plant Y track the reference, which means to keep error 0. Ideally, keep it drive it to 0. So you have 3 terms. The proportional term is proportional, a constant Kp times the error, and integral term Ki times the integral from 0 to t et, and finally the derivative term. I think I made a typo here. The integral is on a variable tau. The upper bound is the upper limit of the integral is t. So here's the effect of the proportional term. Increasing the Kp causes faster response because you're correcting for the error in a more sensitive way. So Kp times error is your control input. So larger Kp means that you are correcting in a more, responsive manner. So faster response from K equals 0.5, the red line. That's the okay. First of all, this is a response to the step input, the reference. Suppose the reference signal goes from 0 to 1 at time instant 1, and then the controller's goal is to control the system so that the output signal track the blue reference signal as closely as possible. So if you adjust the controller gain Kp, if K is 0.5, you have the red curve as the system output, the response. So it's called underdamped system. So for K equals 1.1, the green response, so it looks better because it tracks the reference signal after time 3, whereas for the K equals 0.5, it's underdamped, so it tracks the signal after maybe times 7 or 8. So obviously k equals 0.5, the performance is not satisfactory. K equals 1.1 is pretty good. If you have k equals 1.6, you have the purple curve as the response. You can see that there's a large overshoot, and then it oscillates a lot around the reference signal. So then it means a faster response because you're responding to the reference signal very fast. As soon as it goes from 0 to 1, you're responding to it, but have bigger overshoot and larger oscillations. Think of the car as oscillating around the center of the lane very violently. That's the underdamped situation. So I think I said something wrong. So k equals 0.5 is overdamped, and then k equals 1.6 is underdamped. Yeah. So underdamped, violent oscillations; overdamped, slow response; and critically damped, that's just right. So for this figure, I think there's no critically damped case. Critically damped should track the reference very fast, and there's no oscillation. Something like this. That's critically damped. So in any case, you have a smaller but non-zero steady state error with P control only, and system may become unstable by increasing Kp. So what's the effect for the integral term Ki? So Ki takes into account history of tracking error and eliminates steady state error. Typo steady state. So so it's integrating the error starting from time 0 and compensating for that. So increasing Ki increases overshoot. So Ki equals 2, you have larger overshoot, but it's more robust to disturbances. So higher eigenn causes overshoot and oscillations. Lower eigenn causes slower convergence, slower elimination of steady state error. And good eigenn achieves a trade-off. You have fast convergence with no oscillation. The figure compares Ki equals 0.5 versus Kp equals 1, Ki equals 1, Kd equals 1 versus Ki equals 2. So for derivative term, the coefficient Kd, so if you increase Kd, it has the effect of reduced overshoot. So Kd from 0.5, the red response to 1 and then to 2, you have reduced overshoot and faster response. So you have low dgain, underdamped, high dgain, overdamped, and good dgain is critically damped. I think I put the wrong figure in here. So this figure is captured from the screenshot of the video. So I think I put D gain in here. That should be, oh, okay. The P gain should be like this. Yeah. Let me see. Yeah, that's right. So sorry for the mistake. So the P has this low, medium, high, and I has low, medium, high, and D low, medium, high. Okay, so that's the effect of the PID gains, KP, KI, and KD. So let's look at an example of vehicle lateral control as shown in the video. So longitudinal control is easy. You just control the throttle and brake to control the vehicle speed. Lateral control is a little bit more tricky because the vehicle is so-called non-holonomic, which means that you cannot move sideways directly. You must turn your steering wheel to move sideways. So it's a little bit more tricky. So let's look at lateral control. So suppose you have a vehicle, a box, traveling on the road. So the center line is the yellow line, and the lane, its lane is down. This is its lane, and the dotted line is the center of the lane. And the vehicle has state of a tuple. One is D, distance to center of lane. So I think I said something wrong. So this is center of lane. The yellow. Yeah, okay. Yes, the yellow marks the center of the lane. The dotted line here is just just to show the angle. So the distance to the center of the lane, the D, and the heading angle, theta. So the reference trajectory is dref theta ref equals 0, 0. That is, you are right on the center of the lane with distance 0 and heading angle 0. So you're traveling straight ahead on this center of the lane. That's your reference trajectory. But your vehicle is now deviating from the trajectory. You have a non-zero D and non-zero theta. And your goal is to control the vehicle so that it goes into this reference trajectory. So the assumption here is that the vehicle has constant speed V reference, VR. So the only control input is ut equals theta dot, the rate of change by steering, rate of change of the heading angle. So we assume a perfect sensor state measurement estimate. That is, we get a d hat, theta hat as the state estimate of the actual vehicle's state, d and theta, and we assume they are equal. So there's no sensor and no estimation error. And d ref, theta ref is 0, 0. That's the desired reference trajectory. And controller outputs a tuple to the plant. So ideally, realistically, you should control both the steering and acceleration. But in our case, we assume a constant speed. So the only real control input is the rate of change of the steering angle, theta dot. Notice that here we're assuming that we're controlling the heading angle theta directly. In reality, we have a real vehicle. The steering wheel's angle is actually different from the vehicle turning angle. So there's models for mapping between these two is dependent on vehicle speed also. So if you turn your steering wheel a lot and the vehicle speed is slow, then as compared to turning your steering wheel a lot with a high vehicle speed, the actual turning angle of the vehicle is different. But we're ignoring the details. We're assuming that you can directly control the vehicle angle, the heading angle. So any questions about the setup? So this is a linear system, has a linear dynamics. So the dynamics equation is system state. This is x dot equals a matrix. Typically, it's called A matrix times X plus B matrix times U. Here, X is a vector of two elements, D, which is distance to the center of the lane, and theta, the heading angle, and U is a single element, the heading angle change rate. So if you multiply out the matrix multiply, you get d dot t equals VR times theta plus 0. So so VR so the vehicle speed VR times sine theta, that's the projection of VR on this vertical axis. So somehow when I use my pointer, I get this weird effect. But in any case, you can see that you are projecting the vehicle speed onto the vertical axis to get the speed that the vehicle is traveling laterally towards the center of the lane. So that's why the d is equal to VR, d dot is equal to VR times sine theta. However, sine function is a nonlinear function, and PID can only handle linear systems. So we make an approximation and assume sine theta is equal to theta, assuming theta is small. So therefore, we have a linearized kinematic model. And then the theta dot, if you multiply out, theta dot equals u, which is exactly our definition here. So that's a linear system model. And then we want to design a P controller. U equals K times X. Both are vectors. So KD times D plus K theta times theta. And then you plug in the U into the system dynamics equation, you get a closed loop dynamics. The top is unchanged because you have a 0 here, and bottom you have this here. So in my PowerPoint, the second level indentation is indicated by this dash. So it's not a minus sign. Just pay attention. So this is the closed loop system dynamics with the P controller gain in it. So the reference trajectory is d ref theta ref equals 0, 0. We want to travel along the straight path with no with heading equals 0. So therefore, the error signal is reference minus the actual measured signal equals minus, because you have 0 here. And aerodynamics will simply take derivative with respect to time. E dot equals minus these two dots, d dot, theta dot, and you plug in the system dynamics, closed loop dynamics here. You get this, which just adding a minus sign in front of every matrix element. So this is your aerodynamics, how your error evolves with time. And your objective is to drive the error to 0. That is, you want to design these two controller gains to drive it to 0. Okay, any questions? So one approach of control design is pole placement. This is not covered in the course, so I'm not going to explain it either, because it'll take at least a few classes. But I'll just briefly go through it. You don't have to understand it. So the closed loop poles can be derived by solving the characteristic equation here, and with the solution denoted here. And to have a critically damped dynamics, that is the good scenario we saw before. Good tracking performance with no oscillation. You need this equation solution to have repeated real roots. That is, you need to have this part equal to 0. And then you derive this relation of KD and K theta. So you choose K theta empirically and derive KD from this relation, so that your resulting dynamics is critically damped. So let's safely skip this part, just assume the knowledge of this particular equation relating KD to K theta. Now, we have a additional step of, remember we made an approximation. We have assumption of sine theta equals theta, small angle approximation. So to keep it valid, that is, keep the vehicle's heading angle small, we impose a threshold, theta threshold, and make sure that the theta's magnitude is always less than the threshold. So our closed loop dynamics is this equation, which is this particular theta. This closed loop dynamics. If you take out the theta dot term and theta term, you have theta dot equals KD times D plus K theta times theta. So that's your theta dynamics. But instead of D, you change it to this formula, which imposes a upper bound on the D. So this part is I shouldn't say equal here. I should say change to. So this sat function essentially imposes a lower and upper bound on this d. So whenever the dt exceeds the upper bound or the lower bound, it simply replaces its value with the lower bound and upper bound. So this is to ensure that even if the vehicle is very far from center of the lane, even though d is very large, do not change the heading angle theta too fast. Keep the theta dot small by imposing the upper bound on this dt in the equation here for determining theta dot. So the dth is set as this formula, k theta times theta threshold divided by kd and then absolute. So as the theta threshold is small, so to keep the small angle approximation valid, if you want to impose the constraint, theta threshold should be pi over 6, then you compute d threshold with this formula. So this formula ensures that the first term never exceeds the magnitude of the second term. KD times this term does not exceed the magnitude of k theta times theta. I think it's a rule of thumb, not a hard guarantee. So even if you impose this constraint, it affects theta dot. I don't see how it directly can constrain theta. So I think it's just a rule of thumb to make sure that you don't turn too fast. So based on intuition, if you're very far from the lane, center of the lane, you should turn very. You should make a very sharp turn, but that might violate the small angle assumption. So you should turn smoothly and slowly to ensure the small angle assumption holds. Okay. So that's the end of our case study for PID control design. Let's briefly review what we did. So we have a linear system model. That's the plant dynamics. And then we want to design a P controller. We don't have I or D. We only have P term. And then we need to determine the two controller gains, KD and K theta, to drive the error signal to 0. To do that, we derive error dynamics, which includes KD and K theta in it. And then we use a method called pole placement to derive the KD and K theta, their relationship. And finally, we ensure the small angle assumption approximation is valid by imposing a upper bound on how much dt can be considered in the theta dot calculation. So any questions? So in this PID control design, we made many simplifying assumptions. We did not consider estimation uncertainty due to measurement noise. So we are assuming perfect state estimation. D hat, theta hat is equal to d theta. We are assuming estimation latency is 0. So time from measurement to state estimation available to the controller is neglected. So we are not imposing any constraints, for example, actuator limits. So we may need to impose a maximum curvature radius to simulate a real car. A real car may not be able to turn very sharply. And we are assuming discrete we're not addressing discrete time, multi-rate, and non-uniform sampling. So our controller design is in the continuous time domain, as done in MATLAB or Simulink, but the actual implementation runs in discrete time, as on the actual ECU with the periodic software tasks. So you need to discretize the controller for and analyze its effect on the control performance. If your controller task runs with a too large period, it may affect your control performance. The continuous time controller is an ideal approximation. And also sampling rate of the estimator may be different from that of actuation. Or may be variable during execution. So all these complicating factors we're not considering. So there are methods, approaches for dealing with these complications, but we are making idealistic assumptions in our control design. So the other well-known control algorithm is called model predictive control, MPC, also called receding horizon control. So you choose a prediction horizon P, and I think I need to modify this part. Yeah, this one is more accurate because the so you have two horizons. One is a prediction horizon M. One is a control horizon P. So you look ahead the prediction horizon M and solve an optimization problem to obtain a series of sequence of control inputs, UK up to U K plus P minus 1. So your control horizon in this case is smaller than the prediction horizon M. And then that's your control input at each time step. K is here, K plus 1, K plus 2, K plus 3. And here it's called input trajectory, but it refers to the computed control inputs, not a state trajectory. So even though they call it trajectory, it's not the reference trajectory, it's the control input sequence. And then you apply the first control input you computed, UK, and then you move to a time K plus 1. And then you redo the computation to get another sequence of control inputs, K plus 1, and so on up to K plus P. And then you apply UK plus 1 and throw away the rest of the control input and move to K plus 2. So every time you go ahead for one step and apply the first control input you computed, throwing away the rest, and then move ahead one more time step. So that's why it's called the look ahead control with limited horizon. So the reason that I didn't do it correctly here is because you have two horizons here. Prediction horizon M and control horizon P. And then you solve optimization problem over the look at time window K plus M to get sequence of control inputs U while you are in the time interval k minus 1 and k. So you're computing the this is k minus 1, computing the next p control inputs while you're in this time interval. So after that, you apply the first control input UK and throw away the rest. So let's look at one example of a vehicle traveling. It wants to turn left. So the planner module, which we'll discuss in next week, has decided a reference trajectory, blue trajectory, that it wants the vehicle to track. So this blue trajectory is output from the planner and input to the controller. The goal is to track the trajectory, ideally with 0 error, but in reality, not possible due to vehicle dynamics and other constraints. So suppose the vehicle at this point has a certain its heading direction is a little bit to the right. So it's heading a little bit to the right. So the actual trajectory looks like this. It cannot possibly track the blue trajectory exactly. So it's a little bit deviation. So MPC will calculate this series of solve the optimization problem and get a series of optimal control inputs U 0 up to t minus 1. We then look at time window t. Here we suppose these two time windows M and P are the same. Denote t in next slide for simplicity. So suppose the t here is 7. So if t is 7, you are computing 6 control inputs, 0 to t minus 1. And then here's the if you in your MPC model, MPC is model based, so you do have a model of the vehicle. So given the model and the control inputs, you compute the hypothetical trajectory, the red trajectory, which tries to track the blue trajectory, but not exactly. And then you take the first step, apply the first control input you computed, move ahead one step to go into this position, like this. And then you throw away the rest. So the rest are gone. You remove the rest of the control inputs and replan a new set of control inputs with one more time step in the future. So this is a new set of inputs and a new hypothetical trajectory based on that input. And then you take the first input and apply it, and then throw away the rest, and then redo the computation. So is this process clear? So let's look at one example illustration of MPC. So the vehicle is doing online planning and control. The yellow is the reference trajectory from the planner, and the actual the green is the trajectory from running the control inputs U computed by MPC for look at horizon T, I should say based on system model. So if you have an accurate model, the green is more close to reality. Otherwise, it may not. So as you can see, the green tries to track the yellow trajectory, but it cannot. There's always some deviations due to system dynamics. And every time step, you take the first action U from the green hypothetical. So the green is a hypothetical trajectory, and then you take the first control input U from the sequence of control inputs you computed, and then you discard the rest and move on to the next time step. So here's the mathematical formulation for MPC. So the MPC solves the optimization problem at every time step. At time step T, you are trying to compute a set of control inputs from UT to UT plus T minus 1, big T plus 1 minus 1. Big T is the look-ahead time window, assuming that the M is equal, assuming that M is equal to P. So control horizon is the same as prediction horizon, which is typically the case, but may not be unnecessarily. So, and then you have three terms. So this is the trying to drive your, so xj is the difference between the actual state and reference state, which should be minimized with the term, this term. And this is trying to minimize control effort. So U is the control input, which should be minimized with the term this guy, for example, to save fuel. And relative magnitude of Q and R encode relative importance of these two objectives. So if you have a large Q, you're emphasizing fast convergence to the reference. And if you have a large R, you're emphasizing reducing control effort. So these two are really weights of the two objectives. And finally, you have and a term. So you apply control input from T to T plus big T minus 1. And then after the last control input, you arrive at the final state of T plus big T. So I think I need a parenthesis to make it more precise. Yeah, that's better. And so this is a linear objective. Everything linear, just matrix multiplies. And then you have a linear system dynamics, as we saw before. Linear matrix A and B. So for this kind of a linear MPCs, it can be solved analytically with this P style feedback control law with something called linear quadratic regulator, which we will not discuss. For nonlinear MPC, you have a more general cost function, which may be nonlinear. So this is a special form of the of this cost function, and then you have a more general system dynamics, which may be nonlinear. F may be a nonlinear function. You may impose constraints on the control on the system state. I think I missed the constraint here. Yeah, should be a U. Control So system state can have a min and max, and control input can have min and max. Notice that you have xj plus 1 versus uj, because you're applying uj starting from time t up to t plus big T minus 1, and you're measuring the state starting from t plus 1 up to a big T plus big T. So the state measurement is always one step behind the control input. And then you may have more general constraints, like arbitrary function of x and u to less than equal to 0, arbitrary function equal to 0. So that's a general nonlinear formulation of MPC. So in general, the solving the optimization problem can be time consuming. And it depends on the horizon. If the horizon is large, you have good control performance, but more computational overhead, and vice versa. Okay, any questions? Okay, let's take a 5-minute break and come back at 4.
So I will need to leave again at 4 o'clock, and could you please make sure that the recording is on for the rest of the lecture?
Okay, let's restart. So I did a little bit update on the slide. So last time I had U0, which is not consistent with the rest of the slides. So I updated the notation to be UT up to UT plus big T minus 1. And at every time step you apply yeah, I should say new set of control inputs, new time t, which is really the old time t plus 1. So I hope it's clear. And next time step t. Okay, yeah. So at time t, you compute ut up to t plus t minus 1, execute ut, and then the next time step t, which is the old t plus 1, you redo the whole thing. So any questions on MPC? So MPC pros and cons. The pros are that it handles constraints explicitly, like all these constraints, whereas PID cannot handle constraints. And it's applicable to linear and nonlinear systems, whereas PID can only apply, it's only applicable to linear systems. That's why we needed to do the small angle approximation to convert sine theta into theta. Otherwise, PID would not work. But if you have sine theta nonlinear terms, you can simply directly apply MPC without the small angle approximation. The cons is mainly the optimizer computation may be expensive. Of course, if you have a linear MPC, it's much more efficient. If you have nonlinear MPC, it's more expensive. And also, look ahead horizon T. You can choose it to trade off between control performance and computation overhead. Larger T leads to better control performance, but higher overhead. I should say, especially for nonlinear. So here's one example of vehicle lateral control. Here we're trying to control a vehicle. We have a cost function of minimizing the deviation from desired reference trajectory, which may be a straight line, maybe some other line, like in the vehicle turn example. Anyway, it's output from the planner. And our objective is also to minimize the control effort with the U term. Constraints are system dynamics, longitudinal and lateral, and tire force constraints. And the MPC takes as input the reference trajectory, road curvature, and heading angle, and outputs longitudinal forces of the tires. And then you have a separate low-level controller that takes the longitudinal forces and outputs the throttling, braking, the longitudinal control, and steering, the lateral control actuation commands to control the vehicle. It's called a bicycle model because it's a well-known kinematic model for a car with so-called Ackermann steering. That is, you can only turn the front wheels, not the rear wheels. So that's a bicycle model. So here's a two-level control scheme. You can also integrate a low-level controller into the MPC. So the overall MPC has more complex models and constraints with increased optimizer computation overhead. So here's the performance result. MPC performance shows the actual vehicle state trajectories, including the lateral motion, the distance x and distance y. I think y is the distance from center of the lane, and x is the distance travel along the road. So you can see it has a sharp turn, perhaps to pass another vehicle, and then comes back to the center of the lane. So the reference, which is blue, and the red is the achieved. They overlap pretty well, so it shows good control performance. And the velocity also overlaps very well, including the longitudinal velocity. At time 0, you're gradually accelerating to reach a target velocity, and lateral velocity, where you are turning in to the left to bypass, to pass another vehicle, and then after you pass it, you turn to the right to come back to your lane. So both the longitudinal and lateral velocities are tracked very well. And the yaw rate figure is also shows good tracking. Low-level controller takes as input the longitudinal and lateral tire forces and generates the actuation commands. So these two forces, Fx and Fy, track the reference input pretty well. Okay. So that's MPC. So which of the below statement about MPC are true? Horizon is a finite window of time. Yeah, that's true. Prediction horizon keeps being shifted at each time step. That's right. You're shifting one step at each time step forward. Full optimization over the time horizon is performed at each iteration. Yes, you are performing full operation, but only taking the first action, first control input. Only the first control action from the optimization is applied at time t. So the answer to the quiz is all of the above. So it may seem to you that you're computing a long sequence of control inputs and throwing away the rest, only keeping the first. But the reason is that if you're solving optimization problem that you formulated here for linear or nonlinear systems, you need to compute all the control inputs from t to t plus big T minus 1 in order to have an optimal solution within a time window big T. So you cannot obtain the first control input only because you're solving an optimization problem within a time window. So therefore, you need to solve the full optimization problem for the entire time window in order to get the first control input to be applied. So MPC originated from the chemical process industry, where they're controlling the chemical plants mixture of different chemicals on the time scale of hours and days. So maybe you run an MPC controller every 5 hours and solving an optimization problem that takes you 40 minutes at every. So your look at time window is maybe 5 hours, and your solving time maybe 50 minutes. So you're solving a large optimization problem with potentially millions of variables. But then after many years, many years before, people thought MPC can be only applied to such slow dynamic systems. But then after many advances in optimization theory, in solvers, so people eventually got it to work on a small, fast time scale of milliseconds, and made it applicable to driving. So I'm going to talk about this PID control lab. So this lab is based on a course on Udacity, which I recommend you to watch because it's a very good course. I just didn't have time to cover some of the material like carbon filters and so on, but it's covered in the class. So let's watch the corresponding videos for the lecture.
So let's now talk about the second part of this lesson called PID control. PID control is a vast field in control, and many classes can be taught about this one subject matter. So what I'll do is give you the very basics and let you implement the very basics, and I promise it'll be fun. You'll be able to drive a car around, and the Google car to the present date uses a version of this exact same controllers that's of course much more tuned to the specifics of our car. But you get to see some of the essence of what it means to control a car. So here's the problem. Consider the following car with a steerable front axle and 2 non-steerable wheels in the back. And say we wish this car to drive along this line, which is the output of our smoother we just discussed. Let's assume the car has a fixed forward velocity, but you have an ability to set the steering angle of the car. How would you do this? You would keep the steering constant, you could give random steering commands, or you could set the steering angle in proportion to what's known as the cross-track error, which is the lateral distance between the vehicle and the so-called reference trajectory. So the third possibility is steer in proportion to this cross-track error, CTE. Choose one of those that you think are best suited to control the car. And yes, you'll steer in proportion to the cross-track error, which means the larger the error, the more you're willing to turn towards the target trajectory. And you can see that this works. As you get closer to the trajectory, your steering will be slower and slower, and you will reach the trajectory. Clearly the other two answers are really bad. A constant steering will put you in a circle and not in a straight line. And random steering, if you ever implement this, is a really bad idea. And believe me, we accidentally did this once. It's a really bad idea.
So that he just motivated the proportional control.
So what you just learned is called a P controller, where P stands for proportional. And here is a really tricky question by which I want to test your intuition. One that doesn't have a unique answer, but it has a best answer. Suppose you do what I just said. You steer in proportion to the cross-track error. That is, your steering angle is proportional by some factor of tau to the cross-track error. What will happen with the car? It never quite reaches the reference trajectory. It overshoots, or either can happen. And my answer is, it actually overshoots. The problem is, no matter how small this constant is over here, the wood eventually will turn its wheels quite a bit towards its trajectory. Then it will move towards the trajectory more and more. And when it hits it, its wheels will be straight, but the robot itself will still be oriented a little bit downwards, so it's forced to overshoot. What this means that applied to a car, a P controller will act like this. It'll slightly overshoot, and that could be okay. The overshooting is very small, but it'll never really converge. It'll be what's called marginally stable, or often just stable in the literature. So I want you to implement such a controller. So here's the code I prepared from you. There's a class robot with which you're familiar. It has an init. You can set the position using the function set, as before. There's steering noise and distance noise. You're familiar with this. There's also something called drift, which we won't use right now, but later on it'll become handy. And there's your move command. All the way you've implemented it before. And I've improved a little bit the printout of the coordinates using floats. I wanted to implement the run command, which takes as input the control parameter that governs the proportional response of the steering angle to the cross-track error. The robot has an initial position of 0, 1, and 0, a speed of 1, and I wanted to simulate it for 100 steps. So here's what I envision to happen. Your robot is initially off the x-axis by 1. I wanted to drive along the x-axis, so the y value is the same as the cross-track error. By turning inversely proportional to the y value, using a parameter tau that sets the response strength of the proportional controller, I want the robot to turn towards the x-axis, drive in that direction, overshoot, turn around, and drive back. To do this, simulate the robot for 100 steps, and use a proportionality term that sets my steering angle alpha in proportion to the cross-track error y. So enter your code here, and when you're done with it, and you run it with the coefficient 0.1, here's the output I want you to produce. It's 100 lines. You can see the robot position starting 1 off in y. It then reduces y over time to go into negative territory. On the right side, you see the corresponding steering orientation, and you can see as you move on, the y coming back into positive territory, and you can see how the robot overshoots slowly around the reference trajectory of the x-axis. So please go implement this.
So this is not the exercise I have in mind, but let's look at the source code, which is just below the video. So you have a class robot in Python, initialize the position at 0, 0, orientation 0. So I think the Y position should be initialized to 1, but anyway, noise, measurement noise is also 0 to simplify the problem. And then you have a move function. So here you also impose a upper bound on the steering angle. If it's greater than the max steering angle, you simply set it to max. And then you apply a little bit of apply some noise, execute the motion, and then this whole part is from the bicycle model kinematics. The details are not important. So essentially, it computes the next position based on your steering angle and velocity. And then these are the functions. And then you have the run method that runs the robot. And then you can plot it. So in this exercise, he wants you to implement a P controller. But I think he gave the answer next.
And here's my implementation. It's really simple. I execute the following loop 100 times. I set the cross-check error to my robot Y. The steering angle becomes minus my control parameter times the cross-check error. I call the move command with the steering angle and the given speed. And I print as an output my robot along with the steering direction. So this simple routine just does it.
So that's a simple exercise.
Let's now modify the parameter to 0.3. And here's my quiz. If you modify the control parameter from 0.1 to 0.3, what happens? It oscillates faster, it oscillates slower, or nothing. Please check exactly one of those. And as we'll see, it'll oscillate faster. You have to spend some time with this, but for the larger value of 0.3, we reach a negative value in Y already here, which is where we've just crossed the line. This is just 13 steps in. Whereas if we revert back to 0.1, then at step 13, we are still 0.6 off. So clearly the control oscillation is much slower and we compensate much less.
So this is when you increase the controller gain, you see more oscillation for P control, as we discussed before.
So the basic next question is there a way to avoid the overshoot? And it would be nice if we could do this, because driving in an oscillating car is no fun. In fact, it makes you really seasick. Believe me, I've been in this car for months on end when we prepared for the DARPA Grand Challenge. And the trick is called PD control. In PD control, my steering alpha is not just related to the cross-track error, by virtue of the gain parameter tau p, but also to the temporal derivative of the cross-check error. What this means is that when the car has turned enough to reduce the cross-check error, it won't just go shooting for the x-axis, but it will notice that it's already reducing the error. So when the error is becoming smaller over time, it counter-steers. It steers up again. And this will allow it to gracefully approach our target trajectory, assuming appropriate settings of our differential gain tau d versus the proportional gain tau p. How do you compute this derivative over here? Well, at time t, this is the same as the cross-check error at time t minus the cross-check error at time t minus 1 divided by the time span between t and t minus 1. In our code, we assume delta t equals 1, so we can omit this. So the difference of the current cross-check error and the previous one is this term over here. And we now control not just in proportion to the error itself, but also to this difference of the error using a second constant tau d. So let's implement this. Now I give the one command two parameters, param1 and param2, and I want you to implement a controller that varies the steering direction proportionally according to parameter 1 and differentially proportionally to parameter 2. Again, run for 100 time step and see what happens. So when I run my new controller with proportionality parameter 0.2 and the differential one is 3.0, then I get a sequence of y values that converge much more gently to 0. And miraculously, as time goes on, they really go down to 0 and stay at 0, which we didn't achieve for the proportional controller. So please write that routine so we can test it. So here's my solution. I build a variable called diff cross-check error, which is my differential, that's set to the momentary cross-check error minus the previous one, which I, in the very first time, initialized to the present one. And then in the steering, I don't just steer proportionally to the cross-check error, but also proportionally to the differential cross-check error times the parameter 2. When I put this in and I run it, it gets exactly the output that I showed you. So let's talk about a problem that often occurs in robotics called a systematic bias. And it goes as follows. When you ordered your car, you believed the front wheels were 100% aligned. But your mechanic made a mistake, and he aligned the wheels a little bit at an angle. Now, for people, that isn't a big concern. When we notice this, we just see a little bit stronger. But let's try this out with our proportional controller. So I'm now adding a line that sets the steering drift to be 10 degrees, which in radians is this expression over here, using the set steering drift command. And I want you to run my proportional controller with parameter 0.2. And for now, we're going to set the differential controller to 0. When you do this, what happens? It works just as before, or it causes a new big cross-check error. Go try it out. And of course, it causes a new error. If I go into my output for 100 steps, I'll find that the y value is between 0.7 and 0.9. So it really added a lot of error. Put differently, the robot oscillates a bit like this, with a fairly constant new offset error due to this bias. And even though the bias was in steering, it manifests itself as an increased cross-check error in the y direction. So here's a question for you that requires some thought, and you can try it out before answering this. Can the differential term solve this problem? Yes or no? And the correct answer is no. Let us try this out. Let's enter a 3.0 for the differential term, run everything, and the y error is still large. It converges now 0.87, but it's still really, really large. So what's the intuition? If you drive a car and your normal steering mode leads you to a trajectory far away from the goal, then what I submit you do is, you notice over a long period of time, you can't get closer. So you'll start steering more and more the more time goes by to the right to compensate this bias. You adjust to the bias. And as a result, when you drive, you'll steer the car this way. To do so, you need a sustained situation of large error. So that's measured by the integral or the sum of the cross-check errors over time. So let's make a new control law where steering is proportional to the cross-check errors before. It's equally proportional to the differential of the cross-check error. But now it's also proportional to what's called the integral or the sum of all the cross-check errors you ever observed. And this term is interesting. If we have a constant cross-check error of, say, 0.8, then the sum will increase by 0.8 for each time unit. And it'll become larger and larger and larger, and eventually it'll correct the robot's motion. So this is called a PID controller. This is the P, or the proportional term, the D, or differential term, and the I for integral, PID. So let's implement this, and the integrated cross-check error is the sum of all cross-check errors you ever observed. Let's implement this in our code. I'll give you an integral factor of 0.004, and let's not worry why I picked those. They're actually wisely chosen, as we'll see in a minute. But let's run our code and now modify your code to also allow for this parameter over here. And here's my solution. I implement a variable int cross-check error outside my main loop, then initialize with 0. I then add to the int cross-check error my local cross-check error, and then I have a controller that steers in proportion to the int cross-check error. And when I hit run, I find that my y variable slowly converges all the way down to 0 or 0.05. I get even faster conversions when I set this parameter to 0.01. Looking down, you can see a little overshoot, but my controller converges to 0.0 fairly quickly and then tends to stay close to 0.0. So this PID controller is kind of the best solution for the control problem at hand. And you just implemented one. Now, here's the big question for you. How can we find good control gains? Where control gains are these parameters tau p, d, and I. Now this is my favorite part of this class. Every one of my students has made it through it, and every one of my students is puzzled why I insist on this, but when they implement it, they get to love what I'm just about to show you. The answer is called twiddle. Twiddle is my favorite algorithm that I used in my entire life. Some people call it coordinate ascent, to make it sound a little more sophisticated. But I'll just call it twiddle, because it really gets to the heart of what's happening. In twiddle, we're trying to optimize for a set of parameters. To do so, our function run must return a goodness. This goodness multiplied by the average cross-check error. So I wanted to implement twiddle so as to minimize the average cross-check error. If that's the case, then the output of run depends on the 3 parameters. So here's how twiddle works. Build a parameter vector of our 3 target parameters and initialize it with 0. Also, build a vector of potential changes that you want to probe and initialize them for now with 1. Then you can run our command run with our parameters, and whatever it outputs is our best error so far. So now we wish to modify p as to make the error smaller. And that's where twiddle comes in. It's a really smart algorithm, I believe. We sequentially go through these parameters. Obviously, you shouldn't write 3. You should write len of p. And first, we try to increase p by our probing value, compute a new error for this new modified p. If this new error is better than our best error, then we do 2 things. First, we set best error to error, and we even modify our dp to a slightly larger value by multiplying it with 1.1. Otherwise, we try the other way. So we subtract dp from p, and we have to do it twice now because we added it before. And then we do the same thing again as over here. I'm not going to write it out, but we check whether the error is better than our best error, and then we retain it and we multiply dp up by 1.1. But if both of those fail, this one over here and this one over here, we set back pi to the original value, and we decrease our probing thing over here. Say we're multiplying it with 0.9. That's the core of twiddle. And what it really does is, it, for each coordinate in isolation, moves our parameter up or down a little bit by this value over here. If it then finds a better solution, it retains it, and it even increments the probing interval. But if it fails to find a better solution, it goes back to the original and decreases our probing interval. We do this entire thing so long as the sum of the dp's is larger than the threshold. So somewhere in here we say while sum of dp is larger than 0.00001. It's hard to read, but I hope you could follow it. This is twiddle. So let me put this into pictures. We have three parameters, 0, 0, 0. And then in the first iteration, we bump one of the parameters up and see if it improves the error. If that's the case, we retain it. Then we go to the second parameter, we bump it up, it might not work, we bump it down, maybe we retain that one, and so on. And now as we keep bumping up, we might find that neither bumping up nor bumping down helps. So we do instead is we retain the original solution, but make our probing interval smaller than before by a factor of 0.9. In doing so, we can zoom in more and more into a detailed parameter until it finally converges. It's a local hill climber, but it happens to be really, really efficient. So to implement this, I've modified the rand procedure to input a parameter vector of 3 parameters. And for reasons that will be obvious later, I have a print flag that I default to false. I have the same initial parameters as before. Speed and error, crosstalk error, integral crosstalk error. I set my drift parameter. And to make it a little bit more obvious what the effect of parameter selection has on my error, I'll set the total number of iterations to n times 2. And when I count the total crosstalk error, down here I only count it from step n on. So I give the algorithm a chance to converge to 0 for n steps where I don't count the crosstalk error. But I'd like to know how the crosstalk error evolves quadratically from step 101 on to 200. If the print flag is set, I set the output here in degrees and not in radians, and I return my average error, the float value. So I want you to write the routine twiddle, and the routine should find the optimal parameters and return them to me. So I want you to implement twiddle with a tolerance threshold of 0.001. When I run twiddle, it shows the parameters over time and the crosstalk error, and this crosstalk error very quickly goes to 0. In fact, after a few iterations, 107 in my implementation, we get a crosstalk error of 3.611 to the minus 17th. And here's a typical control run. You see my x, my y, my orientation. My drift is constant. That's my constant drift parameters. And in the beginning, the error is 195 on average. But after a short amount of time, you'll find that my y error goes down to 10 to the minus 6 and stays there, which means our controller is really, really good in tracking our desired location. And our final control error between time step 100 and 200 is 3.611. So I wanted to implement twiddle. We might change something on the robot setup, but when you run it, it will be such that if you run a full PID controller and find the optimal parameters, that the final control error will be really, really small. And that's what we'll be checking. And here's my implementation of twiddle. This is a routine that you can keep this way for many, many different applications. All it requires is a way to evaluate something that depends on the parameters and gives you a single error that you'd like to minimize. We have 3 parameters in total. I set the parameters themselves to 0, but the deltas to 1. And it's just a counter, it's unimportant. If the sum of dparams is still larger than our tolerance, which we initialize with 0.001, then I go through all the parameters sequentially. I increment it by dparams, find out what the error is. If the error is better than our best error, which I initialized with the initial error, then I keep the best error and I even increment dparams. Otherwise, I try the other direction. Run, find out the error. If that succeeds, I keep it, I increment dparams. And here's my last case. I didn't succeed, so I'm going to set it back to the old parameter vector and decrease my dparams by 0.9. I increase my counter. Here's my little printout command for debugging. And I return the parameter vector. So let me comment out the print vectors over here and play with this a little more. If I run twiddle, compute the best parameters, and then calculate the error using these parameters, and print out the parameters along with the error, I get a parameter vector, and I get an error that's basically 0. Now let's switch off the integral term. And I can do this with a little trick. I just set dparams number 2, which is the final one, to 0.0, as if I already learned the integral term. When I run this, I get a zero integral term, but an error that's somewhat larger than the final error that I desired. And that's because the integral term is really required to drive the error down to zero. Let's also remove the d term and see what happens. And the result is a really large error of 0.55. That large error sustains even if I remove the robot drift by commenting it out. We still get an error of 0.10 if you just have a proportional controller. Whereas if I add in the differential parameter again by removing the dprim1 command, the 0.103 goes down to 5.7 to the minus 11, which is practically zero. So you can see the importance of the d term for driving the error down to zero in the case without drift, and for the integral term in cases for robots with a systematic bias. We play a little bit more with this code for the homework assignment, but this is it for now. Let me summarize. You learned two really important things that we use every day in robot programming, and they were somewhat complementary. First, we talked about smoothing, which took a discrete path and turned it into a continuous smooth path. And then we turned about how the robot can follow this smooth path using a control mechanism called PID. With this, you can actually implement quite a bit of robotics. Well, no matter what robot you have, apply a planner, apply a smoother, apply a controller, and it'll do just fine. In fact, this is about the level at which our DARPA Grand Challenge car won the DARPA Grand Challenge. The Google car itself has a little bit more juice in it. It considers the case that the steering wheel itself is inertia and that the steering wheel is driven by something called torque, not by position. But leaving this aside, you really got a gist out of what's happening in robotic driving. And now you're able to really control an actual robot. Congratulations, that is really, really cool. So here's my second piece of software assignment in controls. And in the class, we talked about how to make a car follow a straight line. We used the line x equals 0, where the cross-check error was defined as the y difference between this axis. We just read out the y value. So now I want to make a more interesting course, a cyclic course, a race course. So here's my race course. It has a radius r, which you can set. And the way I'd like to define this race course is through a half cycle of radius r, same half cycle over here, and the stretches in between I want to be 2r long. So for example, this radius equals 25 meters, then this will be here 50 meters, the whole thing will be 100 meters, and this dimension will also be 50 meters. I want you to program it such that the initial car is stationed right over here, pointed upwards, and then it drives onto the race course like this, all the way around infinitely often. The key in doing this is going to be to set a function. I have already modified for you the function run from our control class to use that cross-check area with the parameter radius, which we're going to set to 25, but I can pick a different value in my testing. And then I've modified a little bit the update over here to maintain the differential and the integral cross-check error. And here's our steering control law that you're familiar with. Instead of twiddle, I'm just going to give you parameters 10, 15, and 0. Those work fine for me. And they're actually the result of running twiddle without the integral part. And then when I run it, I get my output. And here it is. The cross-check error by and large is very small. You can see the steering tends to be on the negative side. Here we're steering in the first turn. Here we're in the straightaway. You can see this by the magnitude of the numbers. Here we go into a turn again, so the turning becomes larger. In all of this, you find the cross-check error to be relatively small, about 0.1 or so, not very much. And this continues and continues. The final cross-check error for the second half of the race is 0.005. So you want this number to be really, really small. Now the tricky part is, when you code this up and code the function CDE, you need a different branch for this area here, for this area over here, this area over here, this area over here. Keep in mind that the robot is going to go in a cycle, so it's going to traverse this one in the opposite direction from this one over here. So good luck coding up the correct cross-check error function. And here's my solution. We have 4 cases. On the left side, if I'm on the left side of the race course as defined that x is smaller to a radius. Then my cross-check error is defined by the distance to the circle centered at radius, radius, minus the radius itself. So this is going to be 0 if I'm exactly on the circle. If I'm more than 3 times over to the right side, I get a circle again, looks like the one before, but now the center of the circle is a little bit further to the right by 3 times the radius as opposed to 1 radius. The rest is identical to the line over here, so I'm subtracting the same radius on the right side. You can't quite see it, but it's there. Interesting are the straightaways. So if my y value is large, I'm in the upper part of the diagram, in fact it's larger than radius, then my cross-check error is the y-coordinate times 2 times the radius, which is the height of the racetrack. If I'm down at the bottom, it's just the y-axis, but really important is the minus sign, because I'm moving in the opposite direction. So for your code to run this correctly, you would have got everything in this routine right. So that finishes my homework assignment. Congratulations, you were able to make a car drive on a racetrack. That is actually quite a significant component of making cars drive. The PID control methodology that you learned today and the smoothing methodology are really, really essential, not just in controlling self-driving cars, but in a great number of other control setups. Thank you for taking the class so far. You learned a lot already. You learned about localization, about planning and control. And we're almost done talking about how to build a self-driving car.
So we saw a lot of confusion in the forums about what.
So this particular lecture on Udacity is talking about, first he talked about lateral control of a car to run along the desired trajectory, a straight line, minimizing the cross-track error, the lateral distance of car's center to the desired trajectory. So here's the function run, where the PID controller is implemented on this line. So here the params array, params 0 is KP, params 1 is KD, params 2 is KI, and returns the robot actual trajectory as 2 arrays, X and Y trajectory. So we'll provide a plotting function for that. And the function twiddle, essentially a trial and error approach to tuning PID controller, as opposed to a more rigorous pole placement approach. So I should say this is really, it's not trial and error. It should be gradient descent. If you're familiar with neural networks, use gradient descent to perform local optimization to go down a gradient. This is really gradient descent to find a local minimum. So remember we did a controller design before with pole placement. That's a model-based approach. This is a model-free. So if you come back to the our controller system controller modeling here, we do have a model here. That's a system dynamics model, and based on this model, we did the pole placement control design. But in this twiddle method, we didn't use system model at all. We don't care about the model, nonlinear, linear, whatever. We just blindly go down the slope, gradient descent, to tune the controller gains, to minimize the error, just like a neural network. We're gradually reducing step of adjustment dp until convergence to minimize the error. So it's another approach to PID tuning, more empirical approach, because sometimes system models can be hard to build. For our toy car, it's very easy. But for a real vehicle, the models can be difficult to obtain or can be inaccurate. So this kind of model-free approach can be very powerful, even though very simple. So the lab assignment is the racetrack control, which he talked about next. So the previous was a straight line. Now we have a circular track. Now the definition of cross-track error is like this. So if it's within the straight line segments, it's distance to the horizontal track. If it's not, if it's on the circular segments, it's distance to the towards center of the circle. So your control objective is to minimize CTE, drive it to 0. So that's the definition of the CTE. And your job is to add twiddle to tune the PID gains based on the racetrack control with added function plot to visualization of for visualization of resulting trajectory. So this is where the source code for track control. Yeah, you just click on start quiz. Then you have the Python source code for the track control, except that he set the PID parameters for you. That's the 10, 15, 0. So you don't have to set the parameters. Now, what I want you to do is to add the twiddle function from the previous exercise to this Python program to tune the parameters with twiddle. And you should submit a Python program with the final PID gains and average error, as well as visualization of the final trajectory with plot function. So if you look in the box, I added a PID control.py Python program, which is my adaptation of the Python program with its added function of a plot, so that you can view the resulting trajectory that your controller produced. So I think I should put, yeah, let me download this racetrack control and pull it on box also, so it's more clear. So okay, here's the summary. For straight line track, he gave the twiddle and used twiddle to tune the controller gains. For the circular track, he gave the parameter controller gains directly without twiddle. Now I want you to take the twiddle function from the straight line track Python program and add it to the circular track Python program to tune its controller gains. It's a very simple exercise of copy and paste code and trying out the controller tuning. Very little programming. And finally, I asked you to visualize the result with a plot function, because in the original assignment, everything is printed out as text. So I added a plot function to visualize it. So I'll try to clarify the instructions more and upload the Word document. But that's the basic idea. Any questions? Okay. So that's all I have for today. Yeah. So I'll send out the announcement when the Word document is ready. Any questions on the course material?
What Word document did you say?
Yeah, so I will write a Word document summarizing what I have here. Actually, the PowerPoint is pretty clear. Yeah. But yeah, I'll make it more clear.
Okay, thanks.
Yeah. So yeah, I should say deadline. Deadline is 1 week from now. Because it's a simple assignment. Okay, so if there's no more questions, happy Easter, right? Yes. Okay. Anyone with questions? Chat? Nothing? Yeah. Okay, guys, see you next week. Any questions, just post on discussion board.
Okay, thank you.
Goodbye.
Have a nice
Thank you. See
holiday.
you.
Happy Easter.